Uh, mm, Good morning, dear students. I welcome you to the third video of module 4. We were discussing about Routh-Hurwitz criteria, Routh-Hurwitz table, and stability comment based on the first column sign change, number of sign change. And while filling up of the root table, while completing the root table, we came across few difficulties. So based on that, we have taken different cases. The first case, what we have seen, where there is no difficulty in filling the table. Comfortably, we get all the elements. We used to compute all the elements comfortably. We absorb the first column sign change. Based on that, stability comments has been given. Second case, what we found, there was the element, first column, first element found to be 0. Other than that, rest all element found to be non-zero. But that was causing a problem in computing the next row element. Prime element was becoming 0. So next row element was very difficult to compute. So what we found two solutions for that. Solution number 1, assuming that 0 to be a very small positive element epsilon, and we could complete the table. Once the table, Routh-Hurwitz table, we could able to complete a conventional technique, that is observing the first column of sign change in the elements. First column sign change we used to observe. Based on that, the stability comments were given. What was the second solution given to the case 2? In case 2, we used to reverse the coefficient. Okay, we used to construct a reciprocal system, and we found that the reciprocal system will not allow the roots to cross the quadrant. It cannot cross the quadrant. The distribution of roots remains same if you have a reciprocal system constructed. So we constructed the reciprocal system by reversing the coefficient, and we found that element becoming 0, that is first element of a row becoming 0, we can avoid. So we can complete the table and we can comment on the stability. So stability remains same, because distribution of roots found to be same for the actual system and the reciprocal system. So we able to complete the, stability analysis for such system. Now we have a case 3 system where entire row is becoming 0. Entire row becoming 0, it's a different case. What we did for the case 2, I cannot extend to case 3. It is a totally different case. Sometimes while making a root table, we find that an entire row consisting of 0. This happens because there is an even polynomial that is a factor of original polynomial. Okay, why entire row is becoming 0? Because there is an even polynomial. Hope you all know what is even polynomial and odd polynomial. You will find that the equation consisting of only even powers, that is an even polynomial. Odd polynomial, only odd powers, that equation will be consisting of. So, because this has happened because there is an even polynomial that is a factor of original polynomial. Okay, this case must be handled differently from the case of 0 in only the first column of the row. That is case 2, what we have done, we cannot extend that to case 3. It has to be dealt differently. Okay, so now we'll take an example. Okay, what is the question here? Determine the number of right half plane poles in the closed loop transfer function. What is the transfer function we have? Take the denominator polynomial. We have s power 5, highest power. So this is the denominator polynomial, that is s square plus 7s power 4 plus 6s cube plus 42s square plus 8s plus 56. So this is the equation we have. For this, we have to construct the Routh-Hurwitz table. And what we have to determine? The number of right half plane poles, that is roots exist to the right half of the S plane, we have to compute. Now I'll try to complete the table. The first row I'll compute by taking s power 5. That is odd positions I'll be taking s power 5, s power 3, s power 1. That's all. So 1, 6, 8, I got it. And the left out, coefficient I have taken in a sequence, I got 7, 42, and 56. Since 7, 42, 56 are multiples of 7, so I removed, I just took a 7 out. Why? Because, it is better to handle smaller values rather than bigger values. That's all. As such, characteristics we are not changing. So, I have just removed 7 as a common out. I got 1, 6, 8 present in the second row elements. Next is s power cube. So while computing s power cube, I got 0, 0, 0. While computing s power 3 row, I got 0, 0, 0. So what to do for this condition? Okay. First, we return to the row immediately above the row of the zeros and form an auxiliary polynomial using the entries in the row as coefficients. Okay. What we have to do, since s power 3 rows has become 0, 0, 0. What I did, I go one row previous to that, I constructed the polynomial. I constructed a polynomial. I call this as an auxiliary equation. Auxiliary equation. So P of S is an auxiliary equation constructed going back one step. Okay. So I have S power 4, correct? S power 4 into 1 plus S power 3, I should skip. S square I get 6S square plus this becomes constant. S power 0. I got an auxiliary equation as s power 4 plus 6s square plus 8. Now we have to differentiate that polynomial to get the next row elements. Okay. So I took that auxiliary equation and I differentiated. Took the auxiliary equation, I differentiated. So I got, 4s cube plus 6 into 2, 12s plus constant becomes 0. I got 0 here. What is the value? I got 4s cube plus 12s plus 0. I'll substitute that here in the s power 3 rows. Okay, I cancel this 0 and I substitute 4, 12, and 0. Okay, you can take 4 common out. Not necessary, but you can do it. So 4, if I take it common, I got 1 here, I got 3 here. Anyway, 0 will remain 0. Okay, what are the entries now? 1, 3, 0. Okay, so now what we have to do, finally we use the coefficient above equation to replace the row of 0. Again, for convenience, the third row is multiplied by 1 by 4 after replacing zeros. As I said, 4 I took it common and now the zeros has been eliminated. Okay, is this clear? What we have to do if entire row becomes 0? If entire row becomes 0, we go one row previous and we construct an auxiliary equation and we differentiate that and we fill up the we will pick up the coefficient of that differentiated equation and we will place it in place of zeros. In place of zeros we will be placing it. Okay, so this is what the solution to the what we call difficulty what we come across while filling up the truth table. Once zeros you have eradicated, next is very simple. You continue constructing the root Hurwitz table. So 0, 0, 0, which we got it, we replaced with 1, 3, 0 according to auxiliary equation technique. So now you can compute the next row. We got 3 and 8. Next element is 1 by 3, 0, 0. Next row element is 8, 0, 0. Okay, as such, you don't find any problem here in completing the table. Now, all the elements in the first column are positive. Hence, there are no right half of, there is no roots in the right half of the S plane. Okay, because there is no sign change. So you will see that there is no, what we call roots to the right of the S plane. Okay. So if I refer the question, what was the question? For the given transfer function, I have to find how many roots to the right of the S plane or how many poles to the right of the S plane. So what is the conclusion? Since there is no sign change, so there is no roots to the right of the S plane. That's all. Okay, we have the next question. Determine the stability of the system for the given characteristic equation. Okay, so equation is given. For this, we have to, what we call stability I have to determine. Okay, where K is an adjustable loop gain. Okay, so what's the job? Construct the root table. Okay, take the equation given, construct the root table. So first two rows you have to fill up by looking into the characteristic equation, and these element has to be computed. Okay, that is 2 into 4, 8 minus K into 1, K divided by this 2. Okay, this is what the equation. The other term is 0 because we don't have elements here in the third column. So now what is S power 0? S power 0 is 8 minus K by 2 into K minus 2 into 0. Okay, you will 2 into 0 divided by 8 minus K by 2. So you will get that term get cancelled, only K remains. So I'll be having K. For a stable system, the values of K must be positive. Here, K should be positive. Now, if I take this term, K should be less than 8. If it becomes 8, what will happen? It will become 0 and you will get that element 0. If it becomes any value higher than 8, above 8 it becomes, then this terms becomes negative. Once the terms becomes negative, system becomes unstable. We will find roots existing to the right of the S plane. So we say that the system is unstable. Okay, so when K is 8, the two roots exist on the j omega axis and the system will be marginally stable. Correct? If it is marginally stable, then we will say that the roots exist on the imaginary axis. Okay, and the auxiliary equation I can construct. Okay, a row preceding to the rows of 0. Correct? If I make it 8, then we will see that this element will become 0. Okay, so I will say that the entire row becomes 0 now. So I will go one row prior. I'll construct an auxiliary equation. I'll differentiate that and I'll get the coefficient. Okay, so I will get the coefficient. Okay, the order of the auxiliary polynomial is always even. Order of the auxiliary polynomial is always even. You can refer the previous example. You will get to know that auxiliary equation will be always constructed to the even polynomial and indicates the number of symmetrical roots. Symmetrical roots pairs. Always, symmetrical roots pairs will be existing. Okay, because even polynomial we will be getting as an auxiliary equation. So you will see that only the what we call even power exists, and you will see that symmetrical root pair exists. So for this question, what is the answer? We have to determine the stability of the system. We found that the system is stable for the values of K between the range 0 to 8. If it is less than 8, it is unstable. If it is greater than 8, again it is unstable. That is what the comment. Now let us take a few more cases where the entire rows will become 0. Okay, we will see different cases now. One more case. An entire rows of zeros will appear in the root table when a purely even or purely odd polynomial is a factor of original polynomial. Okay, as we have seen priorly, when there is a situation occurs that is a even polynomial or an odd polynomial will become the factors of the original polynomial, we come across entire rows becoming 0. Okay, say for example, s power 4 plus 5s square plus 7 is an even polynomial. It has only even power of s. Okay, when do we call an equation as a even polynomial? If powers are only even. Even polynomials only have roots that are symmetrical about the origin. This is very important point we have to understand. Even polynomial will have symmetric roots about the origin. Okay, symmetric roots, let us consider different symmetric roots possible. You can have a pair on the imaginary axis which is symmetric about the origin. You can have a pair of roots on the real axis, one to the left, one to the right, which is symmetric about the origin. Even that can happen. And you can have the other option, that is, the quadrantal, we call it as quadrantial roots. Okay, it can take four different quadrant positions it can take. Even this can happen. Okay, symmetric roots can happen in these three conditions. I repeat, the first one is the roots are symmetrical and real. Roots can be symmetrical and real. The roots are symmetrical and imaginary, that can be possible. And the roots are quadrantial, we call it as. Okay, in each or combination of these cases will generate an even polynomial. Okay, when even polynomial can be generated, if any one case is true, even polynomial can occur. Even polynomial will occur. So once even polynomial will occur as the factor of the original expression, if any one situation exists, then we will found an entire row becoming zero. Okay, so whenever you come across a situation of entire row is becoming zero, then there will be any one situation existing. Because of that, we will be getting even polynomial as a factor of the original polynomial. So you have to interpret the root positions this way. Okay, so the row of zeros tells us the existence of even polynomial whose roots are symmetric about the origin. This is the first point we have to understand. Whenever an entire row becoming zero, then we have to conclude that there will be symmetric roots existing about the origin. Okay, some of these roots could be on imaginary axis. It can be imaginary axis. On the other hand, since j omega roots are symmetric about the origin, if we do not have a row of zeros, we cannot possibly have j omega roots. Okay. So I repeat once again, in other hand, since j omega roots are symmetric about the origin, if we do not have a row of zeros, we cannot possibly have j omega roots. Okay. On imaginary axis, if we are getting a symmetrical root, means you have to encounter a situation called entire row becoming zero. If you don't have this situation, there is no possibility of occurrence of a pair of poles lying on the imaginary axis which is symmetric about the origin. That is not possible. Another characteristics of root table of this case is that the row previous to the row of zeros contain even polynomial, that is the factor of the original polynomial. Okay, this is very important point, that is entire row becoming zero indicates that auxiliary equation constructed will be always having a even polynomial. Okay, it will be a even polynomial. Finally, we can say that everything from the row containing the even polynomial down to the end of the root table is a test of only the even polynomial. Okay, see what we wanted to say here. That is our entire row becoming zero happened, and we constructed an auxiliary equation and we tried to complete the table. From that zeroth row to the below, from zeroth row to the below, that is even polynomial down to the end of the root table, is a test of only the even polynomial. It is just like, you are doing this stability test for only that even polynomial, not for the entire characteristic equation. It is only for, that section, the below section, that is below to the entire row becoming zero, that below Ruth Hurwitz's table section, will talks about only the even polynomial characteristics. It talks about only the even polynomial characteristics. That's all we wanted to infer at this point. Based on this concept, we have an example. Here, what you have to learn is how to comment on the stability and how to conclude that roots to the right of the S-plane, roots to the left of the S-plane, and number of roots on the imaginary axis. Question is, for the transfer function, tell how many poles are in the right half plane, in the left half plane, and on j omega axis. Transfer function is given, such a huge lengthy transfer function is given. Let us construct the Routh-Hurwitz table. Okay, so if you start constructing the Routh-Hurwitz table, you come across a situation at s power 3. S power 3, you got a situation where all the rows will become 0. All the rows will become 0. That is, entire row becoming 0. So how to handle this situation or this difficulty? Go one row previous to that, construct an auxiliary equation, differentiate that, pick up the coefficient and place it in the 0th row. We have done it so that we could able to complete the Routh-Hurwitz table. Once the Routh-Hurwitz table is completed, we have to observe the first column elements. First column elements, you have one sign change, two sign change here, correct? From +1 to -1, -1 to +1 is what happening, two sign change. Two sign change happening where that is prior to the s power 4. S power 4 plus 3s square plus 2 is the auxiliary equation constructed. Previous to that, we found that sign change happening. So what I can say, previous to that higher power, higher to this s power 4, I have two roots to the right of the s plane. Okay, so that 2 you take it out. So what is the highest degree of the equation here? Highest degree of the characteristic equation is totally 8. Out of 8 roots, I will say that the 2 roots, sign change happening where? Sign change happening between s power 8 to s power 4. Between this section, sign change happening. So I can say that in this region only you have 2 roots to the right half of the s plane. Now, s power 4 and below, s power 4 and below, there is no sign change. S power 4 and below, there is no sign change. What is the inference? You will not be having any roots to the right half of the s plane. Okay, no root exists to the right half of the s plane. So totally we have to have 4 roots, correct? From auxiliary equation to below, auxiliary equation, from that point below, I want to get 4 roots. Okay, 4 roots should exist. Out of 4 roots, how I can conclude where all these 4 roots can occur? Since it is an even polynomial, there is a chances of one pair on imaginary axis, correct? One pair has to be on the imaginary axis, and since two roots are here, the rest of the roots should be to the left of the s plane. Okay, so that is what the conclusion we will make it here. That is, how do we now interpret this Routh table? Since all the entries from the even polynomial at the s power row down to s power 0 row are a test of even polynomial, we begin to draw some conclusions about the roots of the even polynomial. As I said, the stability comments we will be giving. No sign change exists from s power row 4 down to s power 0 row. Okay, thus even polynomial does not have any roots to the right of the s plane. As I have concluded, you will not find any roots after s power 4 to the right of the s plane. Since there are no right half plane poles, no left half plane poles are present. That is, number of left half plane poles present because of the requirement of the symmetry. Okay, so because entire row has become 0, since no sign change happening, so if there is no roots to the right, there is no roots to the left. Okay, so that is on the concept of symmetry. We can say that the number of what we call no roots to the right of the s plane says that there is no roots to the left side because of the symmetry, because even polynomial is what we got it as an auxiliary equation. So conclusion one, we can say that to the right no roots, definitely to the left no roots. To the right no roots, how can I say? Because from s power fourth row to s power zeroth row, there is no sign change happening in the first column, so there is no roots to the right, so definitely there is no roots to the left below that. Okay, hence the even polynomial must have all four of its poles on the j omega axis. Okay, so all the four we found it on the j omega axis. That is what the conclusion we do it. Okay, these results are summarized in the following table. Okay, right half of the s plane from s power 4 and below we don't have because of the symmetry. To the left we don't have, to the right we don't have. Whatever the four roots we are supposed to have, we have it on the j omega axis. Okay, if I look into the higher order, there was two sign change happening, so I have two to the right, so obviously the other two should be to the left half of the s plane. That is what this table says. So totally what we have two to the right half of the s plane, two to the left half of the s plane, and we have four on the imaginary axis. Okay, so this is how we comment on the stability of the system based on the auxiliary equation. We conclude the roots, distribution we can say, exact position we cannot say. The distribution we can say this way. Okay, with this I'll conclude this Ruth Hurwitz's criteria. I'll continue with root locus from the next class. Thank you.